morning session of the third day. Let me just, since there are not too many people, all of you are from, colleges in Mumbai? Science, how many science colleges students are there? Okay. Engineering? High school? High school, okay. 2, 3 of you, okay. So, the first thing I would like to say is, if there is something that you don't understand, I don't need to actually go through all the slides. You just stop me and I'll try to answer your questions, okay? So, let it be more interactive. Okay, so what I'm going to, okay, there are 3 talks, 2 in the morning and 1 in the afternoon at, I think it starts at 2 o'clock if I'm not mistaken. 2 or 2:30? 2:30, okay. Okay, so let's start with this talk about the neutrino, which is a very elusive, but it's a very fascinating particle. Let me start with a part of a poem written by John Updike, which is called Cosmic Gall. Neutrinos, they are very small, they have no charge and no mass. Of course, that no mass is not quite true. It has a very tiny mass and do not interact at all. Well, they do, but very tiny interaction. The Earth is just a silly ball to them, through which they simply pass like dust mites through a drafty hall, or photons through a sheet of glass, and so on. Okay, it's a pretty long poem. I didn't want to put all the lines here. Okay, so this is the plan of my talk. This longish introduction to neutrinos, neutrino oscillations, because this is some phenomenon which is we found out about 20 years ago. Then about the underground lab in India, which we hope to build, the India-based Neutrino Observatory. Then work towards that by building a small model, actually it's just a toy, you might say, as compared to the big magnet that we want to build at Madurai. And then just a small summary. Okay, so introducing neutrinos. Neutrinos were proposed by Pauli to solve the problem of the continuous energy spectrum that we observe in beta decay. That probably all of you know. And so there is a problem of conservation of energy momentum as well as angular momentum. And this was solved in one stroke by hypothesizing a new particle, which of course Pauli was a little hesitant to do, because the particle that was proposed would be very hard to detect. And so that was the reason why he was hesitating. In fact, to solve this problem, Niels Bohr had a much more radical solution. That is, maybe the laws of conservation of angular momentum, energy momentum and angular momentum were not followed in beta decay. But it turned out that Pauli was right. This was the more conservative solution, but he turned out to be right. Very quickly after that, Payals and Bethe, who are these two people here, Payals and Bethe, they showed that the interaction cross-section of neutrinos is extremely tiny. It is about 20 orders of magnitude smaller than typical nuclear interaction cross-sections, which are measured in barns, if you know. And therefore, they said it's too small to detect this cross-section, which is related to the probability of detection, or which is related also to the mean free path. So the mean free path is so long that it hardly interacts, and therefore, for instance, the mean free path is 10 to the 16 kilometers for a MEV neutrino, and therefore the interaction probability when it crosses the Earth is just 10 to the power of minus 12. So only 1 part in 10 to the 12 particles will interact if you make it pass through the Earth. So you can imagine how difficult it is to detect. Fermi wrote down the first quantum theory for beta decay in 1934. And which of course gave a cross-section which was similar. By the way, this cross-section was calculated in a very beautiful manner, I think. Simple but beautiful, because it used basically dimensional arguments to get this cross-section. Okay, so we now know that all of matter is composed of elementary particles, quarks and leptons. And the quarks interact, of course, to the strong interaction. It is so-called color interaction. But in any case, you can say that these particles interact strongly. And all the particles that we know of, like mesons, like protons, neutrons, they are made up of these elementary particles called quarks. U and D are the ones which are the most common, and they are stable, and they make up neutrons and protons, for instance. The charmed and strange top and bottom, they are quarks which are heavier and they decay. Okay, so they don't live, they don't have an infinite lifetime. Then there are the leptons. The most common one and which we are most familiar with is the electron. That's a lepton. It's part of an atom. The partner to that is the electron neutrino, which was the one first proposed in beta decay, in the context of beta decay. But there are other heavier leptons as well. The muon is the next heavier lepton. So these leptons are charged and these leptons are uncharged. Okay? So the muon has its partner called the muon type of neutrino. The tau has a neutrino which is its partner called the tau neutrino. Then the forces between these particles, there are particles that are exchanged, and they are the so-called force carriers. So we are most familiar with the photon, which is the force carrier for the electromagnetic interaction. The gluon, which is responsible for forces between quarks, strong interaction, the color interaction. Then the Z and W bosons for the interaction, so-called weak interaction, which is responsible, for instance, for example, for beta decay. And finally, of course, this is the Higgs boson, the so-called God particle, so named for some reasons, which are probably not entirely correct. But in any case, the Higgs boson is the one that gives masses to these quarks and leptons, but we still don't know how you can get masses for the neutrinos, as we'll come to later. Okay, so the neutrinos, the electron type of neutrino, although it was said that it's very hard to detect and probably will never be detected, just 20 years or so after the prediction of Bethe and Piles was indeed detected at a nuclear reactor. And Reynes, of course, got the Nobel Prize much later, about 40 years after. The muon neutrino was detected in an accelerator experiment, not at a nuclear reactor, an accelerator, in '62, and this fetched these three gentlemen the 1988 Nobel Prize. Finally, the new tau was detected in a collaboration again in an accelerator-based experiment at Fermilab. These are some few properties of the neutrinos that might be worthwhile pointing out. The electric charge is, of course, 0. It has a mass which is less than about 2 electron volt by c squared. So we only have an upper bound. We don't know what the exact mass is. As we will see, this mass is also not a single number. If you make measurements, you will get 3 kinds of masses. Okay, that's because of the mixing phenomena. That's because of this phenomena called neutrino oscillations. Neutrinos only interact weakly with matter, of course, apart from the gravitational interaction. Gravitational interaction is all-encompassing. Anything with mass or energy will interact with the gravitational interaction. There's an important property that we do not know anything about these neutrinos, namely whether they are their own antiparticles. For instance, the photon is its own antiparticle. On the other hand, the electron has a partner which is the positron. So the electron is negatively charged, its partner is positively charged, the positron. But as far as the neutrino is concerned, we don't know. They are neutral particles, so in principle they can be their own antiparticle, but they may not. So we don't know the answer to this question, even about 90 years after it was first proposed. If it's its own antiparticle, then it goes by the name of Dirac, else Majorana. The important property that we have, as I said, discovered in the last 25 years is that neutrinos oscillate. We will come to that in the following slides. It is also the second most abundant particle in the universe. Which is the most abundant? Can any of you say? Photon. Yes, you're right. So the photon is roughly about 400 odd particles per cubic centimeter all over the universe, if you average over the universe. And neutrinos are the second in number density, and they are about 300 odd. Okay. Okay. If you want to study neutrinos, of course, you have to know what the sources of neutrinos are. The sun is, of course, a very strong source of neutrinos. If you just look at your finger, the tip of your finger, which is about a square centimeter, through that you have about 60 billion neutrinos passing every second. But you don't come to know of that because they hardly interact. So in your whole lifetime, there might be a neutrino which interacts with your body. Okay? That's the kind of low interaction cross-section that they have. Nuclear reactors, of course, are very powerful sources as well. These reactors, of course, run on fission reactions, and fission fragments which come out in a fission reaction are neutron rich, so they of course beta decay, and roughly each fission reaction leads to about 6 neutrinos. So one can even estimate if a 1 gigawatt electrical nuclear reactor, such as at Coudencolum, for instance, how many neutrinos does it emit per second. Okay. Particle accelerators, and the first use of these to discover neutrinos was the AGS synchrotron, the 26 GeV synchrotron at Brookhaven. But indeed, any of these high energy particle accelerators, you can produce neutrinos. Atmospheric neutrinos also are an important source. They are produced when cosmic rays interact with the upper atmosphere, and the Earth is surrounded by this sheath of atmosphere about 10 kilometers thick. So when cosmic rays, which are mainly protons, they interact with the upper atmosphere, which is nuclei of nitrogen and oxygen, then they produce pions. The pions decay to muons and new mu's, muon type of neutrinos, and then the muons in turn decay because they are also unstable, and they decay to electron muon type of neutrinos and also electrons. So roughly atmospheric neutrinos, you expect about 2 muon type of neutrinos for every electron type of neutrino. Okay, then supernova are also very strong sources. This happens when the star comes to the end of its life, and these are very spectacular events. So suddenly that star lights up and becomes much brighter than what it was before. And the earliest instance which is recorded in history is about 1054. In the Crab Nebula, you have a supernova which exploded, so about 1,000 years ago. And this is so spectacular in terms of neutrinos that 99% of the energy that is coming out from this explosion comes out in the form of neutrinos. Okay? So it's a huge number of neutrinos that come out. And the nice thing is that we have indeed detected these neutrinos in one event, one supernova called SN 1987A. Then I said that there are 300 neutrinos on the average in the universe per cubic centimeter, and they come from the so-called cosmic Big Bang. So but we haven't yet detected them directly, and this is actually an important problem. There are people who have ideas and who are working on things, but we don't have a detection yet. So I'm almost sure that if this is detected, this would fetch a Nobel Prize as well. Okay, so how does a neutrino interact with matter? So there are these various kinds of reactions. A neutrino can elastically scatter off an electron, just like a photon can scatter off an electron. A neutrino can interact with a nucleon to produce the corresponding charged lepton. In the nu mu case, for instance, it would be a mu minus. If it is a nu e, then it would be E minus. These are the so-called charge current quasi-elastic reactions. So this is an example here. A nu e comes in, it interacts with iron. For instance, iron is used in our iron calorimeter. Then it produces a cobalt nucleus, so a neutron has changed to a proton. And then you get a cobalt nucleus and you get an electron coming out. So the detection of a neutrino involves, of course, detection of charged particles, because neutral particles are almost impossible to detect directly. Almost impossible, I say, because there is a way of doing that. But you detect the electron or the muon or the tau particle. As soon as you have a charged particle, we know how to detect it in multiple ways. Okay? The other interaction is, of course, more complicated. There are resonances for nucleons, and there's also deep inelastic scattering. At very high energies, when the de Broglie wavelength of the neutrino becomes smaller than the size of the nucleon, then it can actually see individual quarks which constitute the nucleon, and so you can get scattering from the quarks instead of scattering from the nucleons. This is called deep inelastic scattering. So these are the cross sections. You don't worry about that. If you estimate for a 1 GeV neutrino the mean free path in matter of a typical density of 5, 6 or something, then you get a mean free path of 10 to the 9 kilometers. Notice that this is different from the number that I gave before, but that was an MEV neutrino, and this is a GeV neutrino. Of course, as energy increases, the cross-section increases. That can be shown also again from dimensional arguments. In a detector which is about 50 kiloton of iron, we still have only of the order 10 events per day. It's a very small number, as you can see. Okay? Cosmic muons, by the way, on the surface are about 200 muons per square meter per second. And this is per day. A day is about 3 × 10⁷ seconds. Okay? So a huge background if you were to do it on the surface. So, okay. Neutrino oscillation. So I just give first of all a quote from Bacall. John Bacall, who with Davis actually proposed the solar neutrino experiment, radiochemical experiment, and he was a very a great figure in neutrino physics. He passed away quite a few years ago. So this is a quote from one of his writings. Solar neutrinos have a multiple personality disorder. They are created as electron. He's saying that in the context of neutrinos from the sun. Are created as electron neutrinos in the sun, but on the way to the earth they change their type. For neutrinos, the origin of the personality disorder, as you might call it, the Jekyll and Hyde kind of behavior, is a quantum mechanical process, and it's called neutrino oscillations. So for instance, you start out with a new mu, it goes, as it travels, it can remain a mu, it can go to a tau. So if you measure a neutrino after it's produced somewhere along its propagation, then sometimes you will get a new mu, but sometimes you will get a new tau, sometimes you will get a new e, and so on. But then it comes back to a new mu, and that's why the term oscillation can come back to being a new mu, and then this process continues. Okay, what's the experimental evidence for neutrino oscillations? Okay, the first clear evidence came from atmospheric neutrinos. As I said, these atmospheric neutrinos are produced when particles decay. When protons interact with the atmosphere, they produce pions, and then they decay. Muons, they decay in turn. And so there are roughly 2 muon type of neutrinos for every electron. And this is actually what we see for downgoing neutrinos. Okay? But if you look at upgoing neutrinos, because as I said, neutrinos, for neutrinos, Earth is just like transparent like glass. If you look at these upgoing guys, then you find a ratio of 1. Okay, so this was the surprise, and this ratio actually doesn't depend too much on the models that you use for how you make these neutrinos. First of all, how you protons interact with nuclei, produce how many pions they produce on the average, all that. That this number of 2 is fairly robust, and the fact that you don't see 2 but you see 1 for upgoing was the first evidence for first clear evidence for that. Of course, there were hints about this from solar neutrinos as well. And the great experiment of Davis, and of course, which was proposed by Davis and Bacall, hinted at that, but people didn't believe that result as arising from neutrino oscillations, because they said you don't know enough about the sun. That was depending on an absolute number of neutrinos. Okay. Now, if you go wrong somewhere in the nuclear reaction cross section, if you're wrong modeling of the sun, then this number could be different. So in fact, the particle theorists actually had a critique of this when Bacall said that this is a hint that it is oscillations. They said that if you can get a number right to within a factor of 10, you should be happy. If you're quibbling about a factor of 2 or 3, it surely doesn't clearly indicate that neutrino oscillations are the reason. Of course, it turned out that a beautiful experiment, which was a sort of real-time experiment, showed that the shortfall in electron type of neutrino by a factor of 2 or 3, which Davis had found, which was confirmed by the so-called SNO experiment, Sudbury Neutrino Observatory experiment. It showed that what was missing was recovered when you looked at the so-called neutral current signal. We might come to that. I am not. Okay, so this was a very clear indication, and indeed, both these experimenters got a Nobel Prize in 2015. Kajita for the Supernovae and Art McDonald for the Sudbury Neutrino Observatory experiment. The reactor neutrino spectrum also shows a modulation, and that is again a signature of neutrino oscillations. And finally, of course, accelerator-based experiments such as MINOS, and now there are several NOVA and the JPark to Kamiokande and so on. They have also shown evidence of that. So what is meant by neutrino oscillations? So don't worry about some of this, because some of this may not be from people coming from schools may not be able to follow, but just take it in the following way. Suppose I have a vector in two-dimensional space. Okay, I will represent it by xy coordinates, so I can point a vector. Now, if I have another set of axes which is rotated with respect to this original frame, then I will have a different x and y coordinate, right? But these coordinates are related through what? Through one rotation angle. In two-dimensional space is just one rotational angle. So in a similar manner, the neutrinos can be represented as so-called in terms of their electronness or muonness or tauness, but they can also be represented in terms of their masses. And it so happens that these could be different. So if they are different, but they're the same particle, right? So they can be related through a so-called matrix. In the case of two-dimensional rotation, there's just one angle that comes in, which can relate the xy coordinates in one frame to the xy coordinates in the other. In this case, there are a few more parameters. There are three angles that come in, because there are three of them. So it's like three-dimensional rotation. So then three of them, and then there is also another parameter that comes in, which is the so-called CP violation, but let's not get into that. Now, if you have just two flavor mixing, you can compute using quantum mechanics what is the probability that you start out with a certain lepton flavor, let's say of the muon type, but this is true even for the electron type, a similar thing will happen. What is the probability that it remains of that type? So if you calculate this, it can be shown that it is 1 minus sine squared that mixing angle, 2 theta, times a sine squared some factor times a delta m squared L by E. So L is the propagation length, E is the energy. Now just look at the delta m squared. The delta m squared is nothing but the squared mass differences, okay? m1 squared minus m2 squared. Now, if theta is 0, sine theta is 0, right? So then this will always be 1. Nu mu to nu mu will always be 1. So it will always remain a nu mu, okay? So this happens when the mixing angle is 0. But similarly, if delta m squared is 0, again the same thing happens, that this is identically 0, because sine of 0 is 0. Okay, so you get P nu. And if I were to say P nu mu going to, let's say, nu E or the other flavor, then this is just 1 minus of this. So then it will be just sine squared 2 theta times sine squared this factor, right? So this is the basis of the so-called disappearance experiments. That means if in an experiment you start out with a certain flavor and you look for that flavor, then you are trying to find out how many of them have disappeared. That's the so-called disappearance experiment. Whereas if you looked at the other flavor, then it's called an appearance experiment. So then that appearance is of course just this part, sine squared. Now of course, depending on what you want to look at, it might be more favorable to look at the appearance, or it might be better to look at the disappearance. Both have certain advantages. So that depends on the choice of the experimenter, what he wants to look at and so on. Okay. Now, of course, these delta m squared, as I said, if you can have oscillations only if this delta m squared is non-zero. Now, that was just a case of two flavor mixing. In practice, there are three flavors, we know that. And the delta m squared, since there are three masses, you in principle have the possibility that this delta 3, 2 can be different from 2, 1, okay? And of course, the overall mass also, we don't know, that is also a parameter. It so happens that this delta m squared is is large compared to this one, 2, 1. And this 2, 1 actually is more relevant for solar neutrinos, as it turns out. And we in fact even know the order of this through the so-called matter effect. And so we know that m2 is greater than m1 by a very tiny amount. Notice that this is so many electron volts squared, okay? So the order of magnitude of this is a fraction of an electron volt. And remember, the lightest charged particle that we are familiar with, the electron, that is only half an MeV. So that's about half an MeV, sorry. So it's, let's say an MeV is how much? 10 to the power of 6 electron volts, right? And this is a fraction of an electron. So this is at least 1,000,000 times smaller than that. Very tiny mass. Okay. Now, as it happens, the nu E interacts with matter electrons. And so just as, when a photon goes through glass, it acquires some kind of effective mass, okay? So it interacts with the, it polarizes the medium, and therefore it slightly slows down. So depending on the material, it can slow down more or less. For instance, in glass, it slows down to about 3/4 of its vacuum speed. Okay. If you take materials with a refractive index of 2, then that is even more slowed down. Okay. Now, in general, therefore, these neutrinos can interact, and then these mixing angles actually change. The mixing angles in the matter as they propagate, they change. And it turns out that, forget about all the formula, but just remember that this mixing angle sin squared 2 theta m in matter, m stands for matter, you have a factor here which is a difference between two numbers. Okay. Now, of course, if theta is 0, then of course this whole thing just goes away, right? Because this is 0. So, however, in matter, for instance, if delta 2,1 is positive and A, of course, is positive for neutrinos and A is negative for antineutrinos, if in this case it can happen that for what does this A depend on? A depends on the number density of electrons in the matter that this neutrino is propagating in. So, and also on the energy. So, at some point you can have this equal to this. If that happens, then this is a resonance. So, even though you start out with a small theta, once this term drops out, then this just cancels, then this is 1. And sine 1 is what? Corresponding to theta equal to 90 degrees. So that's a very large, so theta, sorry, is 45 degrees, 2 theta is 90 degrees. So it's a large mixing angle that you can get even if you started out with a small mixing angle. Okay. So you can have large mixing, and this is the explanation that Smirnov, Mikhaev and earlier Wolfenstein had given for solar neutrinos that come out through the sun. The sun is a very hot object, right? But the hottest part is actually at the center, and that's where the nuclear reactions are going on. Now, if you want to peer into that, the only way is actually neutrinos. You can't look at it through photons. There's no way of X-raying the sun in any manner. So, as the neutrinos come out, they will hit this resonance, a place where this delta cos theta is equal to A, and then they will flip. They will become a neutrino of the other type. Once they become a neutrino of the other type, they don't get detected in all the detectors that we have for solar neutrinos. If you have a question, I can answer that later. So that was the explanation for solar neutrinos. Okay, why you see less of solar neutrinos. Okay, so this is a repeat, so I will not go into that. This I have already said. Okay. Atmospheric neutrinos of the type nu e, nu mu, for example, are detected through, as I said, the charge current interaction. The nu e has to go to electron, nu mu has to go to muon when it interacts with oxygen or the nuclei that are there in water. And water is a very good detector because it's very cheap. You can make a 50,000 ton detector at very low cost. However, what is expensive is, of course, the photomultiplier tubes that you have to put around. Okay, I think I'm going somewhat slow, but it doesn't matter. Okay, so the way they identify nu e from nu mu is by identifying the muon and the electron event. Now, electron being light, it gets scattered around. So the Cherenkov light that it produces, Cherenkov light is like the sonic boom in an aircraft which is moving faster than sound in a medium that emits a sonic boom, right? So this Cherenkov is somewhat like that. Okay, there is a particular cone in which it emits light, and so if you can identify that cone, it happens. So if you project that cone of light on a plane surface, you get this ring. Now, the electrons being light, you get a fuzzy ring, whereas muons give a sharper ring. Okay. Now, of course, you might say that when it propagates, it emits these rings, and these rings are, shrinking in diameter. So, how do you identify this ring? Well, you can do that on the basis of timing, because they take time to travel, and light travels differently at a different speed, and so you can decipher this. You can get a ring. Okay. Okay, so this is just the same thing that the observation was that R down is 2, the ratio of these muon type to electron type is 2, and that's what was the conclusion of this. Okay, so these are the photosensors. So it's a huge tank of water, very pure water, of course, because it shouldn't absorb the light, Cherenkov light. To just give you an idea of how much light is emitted, about 300 photons or so per centimeter of travel of the muon. So many are emitted. But then you have to catch these photons with good efficiency. These photomultipliers have typically about 20% efficiency, 15 to 20%. So out of 300, you might only capture 60. But that is if you cover the whole area. You don't actually cover the whole area. And so it's still a task to detect these. And they had to make special photon sensors for that. You can see these photomultiplier tubes. Actually, you can see a photomultiplier tube here, which is just about 50 millimeter diameter, right? This one is 50 centimeter in diameter, so half a meter. So you can see the person here. And so they collect these light quite efficiently. In spite of that, there are about 10,000 or so photomultiplier tubes there, sitting there. You can see. So they are actually going about in a raft and cleaning these, or looking at, if there's some problem with the electronics, they'll fix that. And then the water, as it gets raised, the raft goes up, and then they will look at all the photomultipliers. So, okay, so this is solar neutrinos. I already said that the sun produces. Let me go one step a little ahead. These are nuclear reactions that power the sun. Fortunately, this is a weak interaction. So the P plus P goes to deuterium, which is heavy hydrogen. I hope some of you know that. And this is a weak interaction process. And as I said, fortunately weak, because if this had been strong or electromagnetic, the sun would have died in a few hours. Okay, so the fact that it is weak means that the reaction rate is so slow, it's slowly burning, right? And that's what makes it possible to live for the lifetime that we have, tens of billion years or whatever. And that, of course, allows also life to evolve on the Earth. If it had been so short, there wouldn't have been time enough for life to evolve. Okay, so there are several reactions that lead to neutrinos, and there are various detectors which have detected them. Okay. Now the shortage of neutrinos actually can be fairly robustly calculated also, because if you were to detect all the neutrinos, in fact the most prominent of them are the PP neutrinos. But the argument, of course, was that the chlorine experiment didn't detect the most populous neutrinos, but detected these, and they could be sensitive to reaction cross sections and so on. Okay. So this, as I said already, the solar neutrino measurement showed a deficit. So Homestake mine, the Davis experiment showed a deficit here, factor of 3 or so. The Kamiokande incidentally also measured neutrinos, but in real time, and they also got a deficit. Similarly, there was a GALEX, another radiochemical experiment, which saw a deficit. This was sensitive, by the way, to the PP neutrinos. These experiments weren't. And finally, of course, as I said, the Sudbury Neutrino Observatory showed that if you detect electron neutrinos, you get about a factor of 3 less. But if you use the so-called neutral current process, in which a neutrino comes in and goes out as a neutrino, but albeit a lower energy neutrino. In this case, what they did is they put heavy water. Heavy water, the deuterium has a very low binding energy of only 2 MeV as compared to, let's say, 8 MeV in nuclei. And therefore, it would break that deuteron up, and the neutron could then be counted. So that process doesn't depend on what type of neutrino it is. Electron, muon, tau type, all behave the same way. So they could measure separately all the neutrinos. And indeed, what was missing here was recovered here. So if you looked at all neutrinos, then you get an agreement with the so-called standard solar model of Bacall. Okay. I think I will skip this a bit, because there are also experiments which look at oscillation effects from reactor neutrinos, and indeed one of the biggest such detector is the Combline Detector, which is a 1 kiloton. The Sudbury was a 1 kiloton heavy water, pure heavy water detector. This is a scintillator detector, so it's you get much more sensitivity using that. And it so happened that in Japan, most of the reactors were about 180 or 200 kilometers away from this detector, and so they could get a very nice modulation of the neutrino spectrum. There is a picture of that, but again, I think I'll skip that. The other thing is that this happens, by the way, very often in science. You start out with a certain objective, which of course should be good enough for people to fund you, for the government to pay for that. But quite often you find things which are unexpected, which you didn't anticipate you would be able to do. And in this case, for instance, the bonus that they got was they actually measured neutrinos from the uranium, thorium, and potassium decays occurring in the, not actually potassium, but thorium and uranium, the decay chain. There are also beta decays there, and so those neutrinos were detected. And in fact, the geo neutrino signal was sort of consistent with what you expect, okay, within error bar. Incidentally, the Kamiokande experiment also was like that. It was actually meant to look for proton decay, and neutrinos were a background to proton decay. They didn't find proton decay. In fact, there was an experiment in India as well, KGF. That was the first experiment to look for proton decay. Didn't find it, but the background turned out to be a signal, and indeed it fetched a Nobel Prize, as I said. Okay, again, I will not go through this. Accelerators also can produce pions, just like cosmic rays can produce pions and muons and so on. And this is the advantage, of course, that you can do it in a much more controlled fashion. You can produce pions of a given, roughly a given energy and so on. And so these can be studied, and there are experiments. I will not go into, again, those details. Okay, one of the questions that is still open is, as I said, neutrinos have a mass. There are 3 masses involved. This difference is small. This is so-called delta m squared solar. But in any case, the order is known here. M2 is greater than M1. We don't know whether M3 is greater. This difference is much larger, as you can see, about 30 times larger. This, whether it is on top or whether it is below. Of course, we also don't know the absolute scale. That is something that absolute measurements will tell us. So this is one of the problems that INO can handle, can address. Okay, this again I will skip, I think, because of time. So as I said, the early experiments we tried to measure this, to weigh the neutrino, so to speak, to find out the mass of the neutrino, used beta decays which have which have small q values and which don't have too much of nuclear or let's say complications, other complications as modulation of the spectrum due to angular momentum changes and so on. So tritium, which is the heavier partner in hydrogen. So you have hydrogen, the normal stable hydrogen is 1. There is a small fraction of it which is hydrogen 2, which is deuterium, and there is also tritium. Tritium is radioactive, but it has a very small decay energy. It's only 18.5 kilo electron volts. So this is good for measuring the neutrino mass. The idea is quite simple, actually. If you plot the spectrum of neutrinos in a certain way, then towards the end of that spectrum, if the neutrino mass is finite, if it is non-zero, then the slope of this spectrum becomes infinite. Okay, and this is the handle that is used by experimenters. So if you can very accurately measure that, then you can tell whether the mass. And this is exactly since the 70s or so, people have been trying to look for the finite mass of the electron type of neutrino, or let's say the effective mass in the light of neutrino oscillations. And what they at that time found was that, oops, is it not moving? Somebody has to go there. Or at the battery down, Zalia. Or you can just page down. Okay, so earlier there were small spectrometers. Now to get this tiny mass and to push that limit from 2 electron volt to 0.2 electron volt, just see the spectrometer that has to be. So it has to look at the last part of that spectrum, okay, very carefully. And so you transport the electrons from a very active, very strong source of tritium, megacuries. Okay, these things cannot be handled in a lab. Typical lab anywhere, so they have to be handled in a lab that actually caters to, can handle such huge radioactives. So Karlsruhe in Germany, there is such a lab, and the spectrometer, of course, was built to make sure that in such a way that it could come through in the street it had to negotiate. And this, with all this huge size, it will only improve the bound by about a factor of 10. But who knows, if they find a finite number, like say 1 electron volt or half an electron volt, that will be great, because then we know we can pin down the absolute mass. And of course, if it happens to be less than 0.2 electron volt, then this experiment is not sensitive, so we'll have to devise smarter methods. Okay, next. Yeah. Okay. So quickly, the India-based Neutrino Observatory hopes to build a huge iron calorimeter. Calorimeter because we want to measure the energy of the neutrinos through the secondary particles that they produce. And in this case, actually, it is only the muon type of neutrino that we want to look at, because muons are very easy to identify and to measure. They are very penetrating kind of particles. And one characteristic of this is that, of course, it will be the largest electromagnet in the world, 51,000 tons. And also, it will have 30,000 glass RPCs. So this is a layered detector. There are iron layers, and in between two consecutive iron layers, there is an active detector, which is basically a gas detector made from two sheets of glass. So the glass that you see in windows is exactly the same glass. Okay, you apply high voltage across them. You have to have a coating and so on to transmit that high voltage, and then you put pickup strips on that, X and Y. So the same detector gives you X and Y. What happens is that when a charged particle goes through, it causes ionization, and because of the high voltage, that multiplies. So you get about a 10 to the power of 5 or 10 to the power of 6 multiplication. So if you produce, let's say, 50 electron ion pairs, you get 50 into 10 to the power of 6. So that produces a measurable dip. You get a pulse, so-called, and of the order of nanoseconds. So you can actually pick that up on strips and then process it through electronics. So you need preamplifiers and discriminators and so on. But if you do all of that, and for so many 30,000 into, each of these detectors will have 128 channels. So there are 64 X strips, 64 Y strips. But this is a tracking detector, because if once you get X and Y, you know which layer it corresponds to, you get X, Y, Z. And similarly, as it goes down, you get X1, Y1, Z1, X2, Y2, Z2. So you can construct a track. And the beauty about this detector, and nobody has yet built such sized magnetic detector, is that iron, of course, is reasonably cheap. So you need some material for the neutrino to interact. So this provides that material. But more importantly, or equally importantly, it can be magnetized. Iron can be magnetized. So you can make an electromagnet. If you pass a current, then you can magnetize it. And so there's a way of doing that. And if you do that, then mu minus will bend in one way, the mu plus will bend in another way. So now you can trace back who is the guy who actually interacted. Is it a nu mu or a nu mu bar? Okay. And then we hope to address this question through the matter effects, because matter affects the neutrino and antineutrino differently depending on the order, as I told you, that A changes sign for antineutrino. So you can get the order from there. Okay. So in about 10 years of running, we hope to, or 9 years of running on a standalone, we can get this number. But if there are already experiments going on, if you make use of that information, then about 6 years to say what the mass ordering is at some statistical significance of 3 sigma, but okay, at some reasonably significant level. So this is a big collaboration of about 28 institutions. We hold collaboration meetings roughly once a year, sometimes twice a year. And this is where this detector will hopefully come up near the border between Tamil Nadu and Kerala. Why this? Because this has a high enough mountain, 1 kilometer tall mountain, a little more than that. And it's also seismically very stable. So you don't have many earthquakes there. And also you don't get into trouble with the environmentalists, because there's no big vegetation there, not many animals and so on. Okay, next. Okay, so I already told you why magnet. Why underground is, of course, just to cut down the muon. So there are 2 ways, of course, going underground. Either you go in a mine, which is somewhat difficult if you want to assemble such a huge detector. So it's better at the tunnel. Tunnel technology is now quite advanced. And this was pioneered actually in Italy in the Gran Sasso lab. Okay. Next. Okay, so these are the experiments planned. Of course, the biggest, the beast in that cavern at the end of a 2 kilometer long cavern under the mountain would be this ICAL detector. But there are also other experiments for which R&D is going on. Neutrinoless double beta decay in 12014 that you will hear about in the afternoon from Professor Nanal. Then there is a dark matter search experiment which is being worked on by the Saha Institute-led collaboration called Dino. Interestingly, both of these are comic characters, Tintin and Dino. And then there is also some groups among the universities who want to build who want to place a small accelerator underground to look at cross sections which are of interest from the point of view of nuclear astrophysics. Okay, next. Oh, is this working? Okay. Okay, so as I said, the iron calorimeter hopes to study mass ordering mainly, but also mixing parameters. It will also look at magnetic monopoles, which is another very fundamental problem. But probably we will improve the bounds by about a factor of 4 or 5, but who knows? There might be a discovery waiting there. Also, one can search for anomalous KGF event. There are some events seen in the Kolar gold fields, which have to this day not been explained. So we can address that, either show that yes, such events are real, or they were artifacts. Also, there are several other things that we could do, and this is all, at least most of this is there in a paper in Pramana. The advantage of using atmospheric neutrinos, of course, that provides a large range of energies and large range of lengths, travel lengths. In an accelerator, the source and detector are fixed. Okay, you can only move them marginally, not much. But of course, you can have a slightly wider band of energy. Okay, but essentially they are all fixed. Whereas in this, you have a whole range, so you can explore phenomena that couldn't be. What is the downside? The downside is the flux is limited. Okay, atmospheric neutrinos are not that large in number, of the order of 1,000 to 10,000 per square meter per second. So that's why you need big detectors. Okay. So we thought of building a small detector just to get acquainted with what could be the problems when we want to build the full one. And so these are some of the things that we wanted to look at: performance of the magnet, whether it measures up to the simulation, long period performance of RPCs, including all kinds of things, DC supply, the front end electronics, what happens when you have a magnetic field and a fringe field interacting, and so on. But we also wanted to look at the possibility of using the fact that muons, some of them could stop there, and it so happens that the field is correctly oriented, that this muon can rotate in the, spin, a magnetic moment can precess in a magnetic field which is perpendicular to it. So that can give information about the magnetic field. So there is an independent way of measuring the magnetic field apart from sense loops and Hall probes. So we want to at least try out this method. So we have made some progress in that. The other thing is that, of course, you would like to measure muons and anti-muons, so mu minus and mu plus, at Madurai and compare it with simulations. So these simulations already exist. And this is actually one of the pioneers who did simulations for the Super Kamiokande and Super Kamiokande experiments. So there's a colleague, a collaborator, I know, collaboration member from Aligarh, and he has collaborated with Honda to make calculations of neutrino fluxes, but also muons. So we can at least check those muon part and then maybe give feedback to them to maybe slightly tune up there if necessary. The other thing that we want to do is we want to try out a prototype cosmic veto detector on such a scale. I'll show you now how big is that. Okay, so now some photographs of, so you have iron plates. This is a 4 meter by 4 meter device. Okay, so the plates, the biggest one of them is about 2 meter by 2 meter. So these plates have to be machined. You start out with 4 meter by 2 meter, but they have to be machined nicely, the edges and so on. So that was done in Bhilai. And then you have to, as I said, stack these up and have place where you can slip in these gas counters called resistive plate chambers. So you have to have spacers, and you also have to have pins so that things don't move when you switch on the magnetic field. To energize the magnet, of course, you require copper conductor, and this is so-called OFHC, oxygen-free copper. And this has to be taken out from this spool, so a lot of time went in actually straightening them out and then bending. So the idea is that you, for the coil, you make it in 2 pieces. You make a U like this, and then a C. So you put the U, assemble all the the iron plates, and then when everything is over, then you braze, or actually you might say welding the upper part to the, so C to U, you braze in situ. So somebody has to come and do it. Anyway, this was done very nicely by the BRC group. And then, of course, you have to mount it on a set of pillars and so on. These are just some pictures which show how you put it together. So you put these U sections, then put these plates using a gantry crane, and then when everything is over, then people from CDM, the BRC had come and actually braze these. So you have an induction brazing machine which joins up these through silver paste, and so the conductivity there is very good. No problem, and can also withstand because these are hollow conductors, as you can see. So you can pass water through that, of course, pure water, and so as to cool the coil, so it shouldn't get heated up, and it should not leak. So all that was done. Okay, this is the water cooling system, which is on the outside. of this Hall. And then these are some things to measure the magnetic field. You might have heard of the Hall effect. So the Hall effect can be used to actually measure the magnetic field. So we have purposely put gaps between some of these plates so that you can insert these Hall probes. And that gives a good idea of what the field is internally in the iron. What we need is the internal field. Okay, but you can, using simulations, you can have a mapping of that field to internal field. Okay, and then you also can do it through the sense loop. That means you have a loop, and as you ramp up the field, you know that if you change the magnetic field, there is an EMF across a coil, and you can measure that as well. So these are two independent ways, and you can look for consistency between them. Indeed, they show consistency within a few percent. These are again some electronics. This is the place where glass RPCs were made in a glass company called Saint-Gobain. So they make this float glass, which is used in windows and so on. There are machines to place these buttons which keep the space of 2 millimeter between the two glass plates, and that is all done robotically by a special purpose machine. This is the gas system. This is a closed loop gas system. You have to flow gas of a particular composition, appropriate combination, and then it works. But you don't want to just put in gas and let it go out. So there is a closed loop gas system, so you save almost all of the gas. And then there are various electronics which was developed in TIFR as well as in BRC. Chips also designed and so on. If there are questions, I can address them. So finally, at the end of the day, there are 10 RPCs very nicely packed inside. And the proof of course, before I show you tracks, there is also lots of students who come in, and especially in summer vacation. So last year, for instance, the maximum number was about 30 students, and at any given time during the summer there are between 10 and 30 students, and they get to learn by actually working on the apparatus that we are building. Okay. Also there are lectures and so on, so some of our senior students also give lectures, some of us go there and give lectures. So these are both seniors. This is a senior student who is giving a lecture, and so on. This is part of the interaction with the students and academia. Okay, so now these are some examples of tracks curved one way and curved the other way as well. Okay, so this is a Y position. No, this is the same event. This is almost a straight line. Okay, somehow I didn't get the one with the opposite curvature. Anyway, we have events of both types, and roughly they are equal. Okay. This is with a field of about 1.4 Tesla made by putting a 900 ampere current, DC current. So again this is stopped. Okay, so I hope I have not exceeded my time too much, but so I hope you get a feel for why I didn't say that, but neutrinos are, by the way, something which might help us get beyond the so-called standard model. The standard model, as you know, may not know, the LHC experiments have all showed up things which agree with the standard model. This becomes a little boring. So if you want to progress, there has to be something which doesn't agree, and only then you make progress. And neutrinos certainly, the fact that they have non-zero masses certainly is beyond the standard model, and that hopefully they will give us a window to physics beyond the so-called standard model. And of course, there is this INO, which is would be one of the big experiments in India, and this is a grassroots kind of effort, because it was thought of in about 2000, and there is unfortunately we still have problems with Tamil Nadu, so we have a plan B, and certainly we want to engage aspiring scientists, some of you, and academia in India. Okay, so this brings me to the end. I think this is the end. Yeah. Okay, so this is the mountain at under which this is supposed to come up. Okay, so thank you. So I would welcome questions if you have any.